Thank you very much for joining this webcast today. My name is Srinivas Reddy, and I'm a product manager at MSC.Software. With me today is Doug Malcolm, who is in our engineering services group, and he comes with very extensive experience in complex simulation problems in the nuclear power industry. In today's webinar, we will talk about how engineering simulation can help accelerate the design process and reduce costs in the nuclear industry. We will be focusing on the virtual testing of a nuclear waste cask as an example of how simulation is used to arrive at better designs faster. Let us start with a very brief overview of a nuclear power plant. As most of you are aware, a nuclear power plant works in the same way as a conventional electricity generation plant. The only difference is in the heating of the water used to create steam that drives a steam turbine. In a conventional electric plant, the water is heated by burning of fossil fuels. In contrast, in a nuclear power plant, the water is heated by a controlled nuclear reaction. Of course, that is a simplistic viewpoint, but the internal workings of a nuclear power plant do involve many complex systems which are subject to high pressure loading, thermal gradients, and loads, and should be designed for potential failure impact events from accidents. All of these systems must be carefully designed and engineered with safety as the topmost concern. So how would simulation help with improving design safety? There are definitely multifold benefits to using simulation. First, through the use of virtual prototyping, simulation enables designers to test and evaluate design concepts early in the design cycle prior to the building and testing of costly physical prototypes. This reduces costs by enabling engineers to perform what-if studies on virtual models to accelerate the design process and time to market, instead of using a series of more time-consuming and costly physical prototypes to validate and refine the designs. Cost savings can also be achieved through efficient management of your company's engineering knowledge and simulation best practices learned during the design process. We will talk more about this later during the webcast. Secondly, many design scenarios involve accidents or deliberate acts of terrorism that cannot be physically tested. In these cases, simulation provides a valuable, if not unique, tool to assess the effects of accident or terrorism scenarios to develop the designs to mitigate their effects without physical tests for these types of scenarios. And thirdly, the nuclear power industry is heavily regulated, and the regulatory agencies impose strict requirements on the documentation of engineering processes and data to ensure repeatability of these results and the traceability of data. Simulation process and data management technology enables systematic audit trails of all engineering simulation processes and their associated data, facilitating repeatability of results and compliance with mandated regulatory requirements. For the benefit of those who are not completely familiar with MSC and its solutions, I would like to take a few minutes to introduce the solution spectrum offered by MSC. MSC is the leading global provider of engineering simulation software, services, and simulation process and data management. With over 4 decades of leading presence in CAE and simulation, it has pioneered advances in several key technologies that helped reduce product development costs while encouraging innovation. With well-recognized and industry-leading products like Nastran, Adams, Mark, Dytran, and EZ5, MSC meets simulation challenges in a broad spectrum of applications, including linear and nonlinear statics, dynamics, fluid structure interaction, thermal structural coupling, kinematic, and the dynamics of systems and controls. In addition to providing software for CAE simulation, MSC also offers consulting and services to address challenging problems faced by our customers. Through mentoring and training of our customers, a services group helps them get the most out of their software investments. The services team also helps with automating user processes to get rapid and repeatable results, improving their productivity. At this point, I would like to pass the control to Doug Malcolm, who will go through more details on how MSC's products can be used in the nuclear industry. Doug, please take over.
Thank you, Srinivas. As Srinivas stated, my name is Doug Malcolm. I'm a senior consulting engineer in our engineering services group here in Santa Ana, California. I've been a consultant in one form or another for over 20 years and have had the opportunity to do a lot of very interesting and challenging projects. Many of those were involved in the nuclear industry. Specifically, what I'd like to talk to you today about is some that were in the nuclear power industry and related to the certification of spent fuel storage and transportation casks. For that, I'd like to do first a brief interview of some simulation applications in the nuclear industry and the challenges that they pose. So the application areas for simulation software in the nuclear power industry cover the entire spectrum of MSC's offerings. These include structural, coupled structural, thermal, vibration, impact, fluid structure interaction, types of analysis, among many others. Specific examples pertaining uniquely to the nuclear industry include the design and analysis of reinforced concrete structures, such as reactor containment buildings. We'll talk about that in a later webinar. Equipment such as piping systems involving fluid flow at high pressure and temperature. And again, we'll do another webinar later on with something related to that. And design analysis of critical thermal structural components such as the reactor vessel. These types of simulations must include a variety of loading conditions, including things like pressure, temperature, vibration, seismic excitation, impact conditions, among many others. So today we're going to demonstrate how simulation is used to conduct drop tests, specifically for spent nuclear fuel storage and transportation casks. So let's talk a little bit about the storage and transportation casks in the nuclear industry. Arguably, the most unique aspect of the nuclear industry is the use and the storage of relatively large quantities of highly radioactive material. Even in its spent form, this material is very dangerous and it requires extreme care during handling, storage, and transportation. So today I'd like to discuss the storage and transportation aspects and how MSC.Software relates to those aspects. As per the U.S. Nuclear Regulatory Commission, or NRC, there are two acceptable storage methods for spent fuel after its removal from the reactor core. The first, specially designed spent fuel pools at the individual sites, is currently the most common form of storage. This water pool option involves storing spent fuel rods under at least 20 feet of water, which provides adequate shielding from the radiation for anyone near the pool. And further, the rods are moved into the water pools from the reactor along the bottom of the water canals. And again, this is to always shield and protect the workers. The second, the topic of today's discussion, is called dry storage or dry cask storage. Typically, it's used as the operators reach pool capacity for their wet storage facility, so it's a kind of a second level. Dry cask storage allows spent fuel that has been cooled in wet storage for at least a year to be surrounded by an inert gas inside a container called a cask. The casks are typically steel cylinders that are either welded or bolted closed, and then these steel cylinders provide a leak-tight containment to that spent fuel, obviously a very critical aspect of the casks. Each cylinder is surrounded in turn by additional steel, concrete, or other material to provide radiation shielding to workers and the others around it. Some of the cask design, in addition, are intended for both storage and transportation, and we'll talk about that in a little more detail as well. So here's some images showing a typical cask storage. The casks that are used for dry storage come in several different configurations, but all have the same basic set of components. One, an internal fuel assembly that holds the spent fuel, a canister that contains the fuel assembly, and a cask or outer container with an opening-closing capability to allow loading of the fuel assemblies. These cask assemblies, typically they're capable of holding anywhere from 2 to 6 dozen spent fuel assemblies and can utilize several different construction approaches. They can be steel with some sort of internal radiation moderator, for example, a lead liner or sleeve, or they can also be concrete walled, wherein the concrete cask wall acts as the moderator. In use, they can be stored vertically or horizontally, and you see some images of that there in this slide as well. In some cases, there will be an inner cask that's stored inside a concrete vault that acts then as the moderator. So the elegance of these casks, at least on the surface, lies in their simplicity. No moving parts, no water to pump, no active cooling requirements. Even better, proper design allows the cask to not only act as a storage container, but as the requirement arises, to act as a transportation container as well. Of course, as you can imagine, this introduces a whole new set of design requirements. So the design and performance of the casks that we're talking about here are governed by regulatory regulations created and maintained by the Nuclear Regulatory Commission, or NRC. In Chapter 1 of Title 10, titled Energy of the Code of Federal Regulations, or CFR. For our purposes, we are interested in Part 71, Subparts E and F, the section specifically detailing the necessary tests and requirements for transportation casks. Ultimately, it's up to the manufacturer of the cask to show compliance in the form of evidence presented in documents titled Safety Analysis Reports, or SARs. What types of requirements are dictated by these regulations? Well, as you can imagine, the requirements are quite extensive. And what we're going to do is look at some of those. Before we do that, though, let's first look at the image on your screen. And one of the things I want to point out here is something that we're going to spend a few minutes talking about a little bit later on, so I wanted to talk about it here initially. Notice that the image is shown here in the video and the simulations to come shortly. You'll see what is known as a limiter at either end of the cask. So in the image you see on your screen that says free drop, there's a cask that's being suspended, and at either end there are some large diameter tubes, if you will, on either end. Those weren't shown in the previous images, but they're critical to the design and function and testing of the casks. These limiters are essentially energy absorbers. They will drastically reduce the shock loads that will be imparted to the storage cask during accident-type events. This can be compared to a crush zone in an automotive design or a permanently inflated airbag, if you will. Basically, it's a sacrificial structure meant purely to protect the cask and its internal components. So let's get back to some of the potential accident events. One, probably the most severe of all the tests, a free drop from 9 meters onto a unyielding surface. And you'll see that phrase come up repeatedly here. Typically, it's a reinforced concrete pad of some sort, so it's extremely rigid. Interesting to note here also is the requirement that during the test, the cask must strike this unyielding surface in a, and I quote here, position for which maximum damage is expected. This won't necessarily be obvious. You can imagine that it could entail many very expensive tests. Second type of accident event is another drop, this time from a 1 meter height, but onto a 15 centimeter, roughly 6-inch diameter pin. Again, the specification states that the cask has to strike the pin in a position for which maximum damage is expected. And again, it's easy to see how the number of these very expensive tests could grow significantly. Some of the other tests we'll talk about briefly, fire engulfment, water immersion, both short and long term, and lifting device validation can all be just as equally harsh and must all be treated in some form, either by testing or simulation or both. So what you see on your screen now is a video of actual testing. This gives you a flavor of what we need to do here. And you'll see this will loop through several times, so it gives you definitely a good sense of what you're looking at. This is, again, actual testing of several different cask designs being subjected to tests similar to what Part 71 specifies. I should note that due to the proprietary nature of these tests, I can't show video of the ones that have been done for some of our customers. This clip was found on the internet, and it's very similar to those tests and the simulations that we're going to show you in just a couple of minutes. You'll notice that several drop orientations are conducted. The first one you saw at the beginning of the video is the end drop, where the cask is dropped essentially vertical. And the second one is the one that we've already kind of showed you. It's what we call the corner drop, where the cask is oriented with its CG, or center of gravity, over the corner of the initial impact. In many cases, this can be estimated to be the orientation that would be the most severe to the cask limiter. as at the moment of impact, this orientation would result in essentially a point load, so extremely high loads and stresses. The corner drop in that video was followed by a typical pin drop, and it'll come back around in just a second. And that shows the pin that we talked about penetrating the limiter and ultimately contacting a cask. The NRC regulations state, quote, the effects on a package of the test specified in Part 71.71, which is the normal conditions of transport, and the test specified in Part 71.73, which is the hypothetical accident conditions, must be evaluated by subjecting a specimen or scale model to a specific test, or by another method of demonstration acceptable to the Commission, as appropriate for the particular feature being considered. End of quote there. You can accomplish that in several ways. The most straightforward, albeit not the least expensive, would be full-scale testing, as you're seeing here. It's clear from this video that the level of effort, support personnel, and equipment goes along with even a single one of these tests, let alone the many tests required for that position of maximum damage can be quite extensive. Alternative to this would possibly be scale testing. However, at that point, you introduce a new complexity. How do we show correlation between the full and reduced scale testing? That's always going to be a question mark in that option. That additional complexity makes this less desirable, although it's still considered a viable option, and probably much less expensive than full-scale testing. Yet another approach would be the comparison of a new design to that of the previously tested and licensed designs. Obviously, licensed designs would have had to met the design requirements initially, and therefore make a good and reasonable starting point for any new designs. Finally, the reason for my discussion this morning is I'd like to show you an approach that applies computer simulations, such as those facilitated by MSC.Software's offerings, to the design and validation of any design. Although computer simulations should not be expected to be fully replace physical testing, it can certainly be expected to limit significantly the number of required tests, especially for designs that are entirely new. Computer simulation can allow many design iterations before any tests are incurred. So the single largest justification for the use of computer simulations can easily be stated as cost. No question about it. Testing can be extremely expensive, and limiting it to the final design is clearly a way to significantly cut costs. There are certainly many other advantages to computer simulations in lieu of testing. Many designs can be evaluated and tested virtually in a very short period of time. So it comes down to time, especially when compared to what it would take to build and test the same number of real and physical casks. Again, even neglecting the obvious cost savings, no hardware fabrication, no transportation costs, no test personnel, and on, there's a real advantage based just on the time savings alone that you can see with virtual testing here. You know, the old adage, what they say is, time is money. It's absolutely true. One final intangible that's often overlooked, though, at these is when making these comparisons is the ability to try things that might not otherwise be even considered the out-of-the-box solutions, if you will. Computer simulations allow you that flexibility and innovation that might just cost too much otherwise. So what I'd like to do now is demonstrate how MSC products and show you some of the work that we've done can be used to help with virtual testing of a cask to meet the regulatory requirements by showing you some of the work that is representative of what we've done in the services group here in the past. So as you saw in the video clip of the actual testing, probably the most severe of all the requirements of these regulations are the drop tests. So let's start with a review of a couple of those. And I should say again here, I should reiterate here that due to the sensitive proprietary nature of these designs, I've chosen to show representative solutions here, but not actual designs. So shown here is a typical corner drop. All of our offerings use finite element approach, and this is no different. So what you're seeing here is a finite element analysis. This happens to be an explicit dynamic simulation using capability of our MD NASTering code, which we refer to as a solution sequence 700. These types of simulations are generally intended for short duration events such as automotive crash or consumer electronic testing, cell phones, video games, etc. This makes it a perfect fit for these cast drop simulations in that it can easily handle the highly nonlinear nature of the strain and strain rate dependencies of the various materials involved in the numerous contacts or potential contacts between all the different components. A few words about this model that aren't necessarily so apparent. First, you'll note that there's no contents. Fuel assemblies and carrier, typically called the fuel basket, are loaded into the cask loosely, and the cask loosely, and therefore don't contribute any significant structural strength or stiffness, so they don't necessarily have to be included in the model. Of course, they're extremely heavy, so we have to account for their weights in some way. For the purpose of this model, the weight is smeared along the bottom walls of the inside cavity of this cask, exactly where the cask walls would bear the weight of the basket if it were there. Second thing that you don't necessarily see so clearly here, but you'll notice that only half of the cask is shown or modeled here. The finite element approach here has the benefit of being able to take advantage of the symmetry of the cask, and that allows us to model only a half of the cask in these simulations. And that always results in significant savings in terms of runtime, disk requirements, and all the things that go with any simulation. Finally, a point of interest that's not necessarily also obvious in this image is the cask limiters here are constructed using a combination of steel plate, and that makes up compartments that are in turn filled with a foam material. And by tuning the plate thicknesses and foam properties, we can tune the cask response and reduce the adverse accelerations that its contents will ultimately experience. Keep in mind that this is obviously a balancing act. Too soft and the limiters might bottom out in certain drop scenarios, and the high ones in particular, while too stiff, and they're going to impart high accelerations to the cask and its contents. So it's all a balancing act here. A couple graphs at the bottom of the page here show a couple of other things that we can extract out of these analyses, notably the displacements and accelerations at the critical locations inside the cask. Once those have been determined, we can apply those to high-fidelity models of the components that are in the internals to demonstrate their respective fitness for service. What you see here is a side-by-side comparison of the video of the actual test and the corner drop simulation. So one thing, keep in mind, as I stated before, keep in mind that the model shown here is, again, just a representative model, not the actual model of this test. But it's still very clear that the virtual simulation very closely reflects the actual test. And in practice, we've seen very good correlation between our simulations and the final physical testing. Continuing on, here's a close look at what the simulation might offer the designer that might not be able to get directly from any test, a physical test. Keep in mind that you get one shot at a physical test. If you don't have your strain gauges or accelerometers in just the right location, you're in a position where you just might miss some data that's critical or at least very important to your design. In this case, what you're seeing is the plastic strain in the steel plate. Anywhere you see a color other than a dark blue, the material is experiencing stresses in excess of its yield point. So what that indicates is you're going to have some permanent deformations wherever you see a non-dark blue color. Based on the level of deformation that the limiter is experiencing, this may or may not be surprising to the designer, but there's certainly value to seeing the distribution of these strains that might allow minor or major adjustments to a design. So remember, our requirement for the testing of these casks to be conducted in what we call a quote-unquote position for maximum damage. Here's a different view, is that orientation of position for maximum damage isn't always clear. We have to do several different orientations. So what you're seeing here, it's very easy to change our orientations. In our virtual world, it becomes very, very simple. In fact, this is the same finite element model as that used for the corner drop, with the only variation between being slightly adjusted event conditions. All of the same benefits that we discussed in the corner drop apply here. This simulation can not only show us whether or not the limiters in the cask will survive, but they're also going to show us with critical load data that we can then use in the virtual testing, again, of the internal components, so we can transfer that data. And you can see that along the other graphs on the bottom of the slide. Okay, and here are some views from the side and end drop for the side drop, showing the plastic straining in the limiter. And again, it's clear that one of the powers of this approach is that there's an extensive data available as to what's exactly happening and how the cask is behaving during the impact event. Okay, so once the cask drop events have been evaluated, it's then a relatively simple matter to extract from those results what the accelerations are and the contents of the cask. And those in turn, we can be used as loading on the internal components, in this case the fuel rod basket. Shown here is a typical basket that would be containing the individual fuel rods within the cask. Each of the empty squares here that are seen here would have a fuel rod in it, but rather than model each fuel rod, we can model the effect of the weight of those rods using methods similar to what we just mentioned with the cask body. Baskets like these are typically constructed of a plate steel in a somewhat loose fashion so that the high temperatures that the fuel rods can generate don't induce high thermal stresses. From a simulation and analysis point of view, this means that there can be significant amounts of sliding in contact. And again, our offerings, MSC offerings, handle this quite well. The smaller of the two images is the basic finite element model, while the right image here shows the deformation as the basket is subjected to the high G loading of the drop event. So for the baskets, this is imperative to know the levels of these deformations and the potential yielding of the material. We want to make sure that the fuel rods don't get pinched or trapped in there, as we may still need to extract these at some point in the future. Another detailed image of that same basket. Here's the detailed stress within the basket from that same G loading. And as you can see, the simulation allows a level of interrogation that would be difficult in a physical test. Essentially, what this approach allows us to do is a kind of a post-mortem at any point in the basket after the test. While if we're doing a physical test, we might have to guess where those critical locations are so that we could then apply any instrumentation for later evaluation. Here's the lid. These casks have to have, as I mentioned, an open and closing capability. Typically, the drop models that we showed you before might not have the level of detail of the closure systems, whether that's bolting or welding, that might be desired. So we handle this in a manner similar to that as we handle the internal contents, and that's by extracting out the loads from the cask drop model and then applying those loads to these detailed models. In this case, the bolting closure of the cask is being evaluated. The model on the left is used in this case for the end drop. Okay. To determine the deflections for both the primary, the thick internal lid, you see it in green there in the lower left image, and the secondary lid. As you can see by the red color of the thinner secondary lid, and that indicates a higher level of deformation or stress, tends to deform more than that of the primary one. That's not an unexpected result, but it's certainly a good confirmation of any previous calculations and of the design regardless. Again, here's a high-resolution picture, and you can see the level of detail here of what the stresses are in the lids that allow the designer to evaluate his design. In this case, good engineer judgment probably would have predicted the high stresses at the center of the lids, but the evaluation of the stresses at the interfaces between the lids and the cask body is clearly not so evident. We talked about a number of the different requirements in the regulations earlier, and here's a couple more. This one, among those, I'd like to show you just a couple more here to give you an idea of the breadth that we have here at MSC. Shown here is a couple thermal structural simulation of the cask during shipping. The heat generation from the rod still generates enough heat that it can be of concern, so we have to consider this. In this analysis, we can calculate the temperatures throughout the cask. Those are shown in the upper image and must meet our Part 71 requirements shown in this slide, in this case a maximum temperature of 122 degrees Fahrenheit. So the temperatures in this requirement are the real focus, but it's also important here and interesting, I think, to recognize that these temperatures can easily be applied to the cask and its contents through a thermal stress or coupled analysis. The bottom image here shows you the results of that type of an approach and represents the stresses in the cask due to the temperatures and the differential thermal growth throughout the cask. Yet another requirement, fire engulfment, and requires the cask function to meet requirements when subjected to a potential fire event. And these regulations characterize this as an 800C event for 30 minutes. In this case, then, because it's time varying, we need to conduct what we call a thermal transient or time varying analysis. So this shows us how fast the cask and its contents are going to heat up and ultimately cool down. Shown here also is a video of an actual engulfment test, as well as the typical thermal transient results in which we can see that temperature rise and then start to fall off after the duration, the 30-minute duration. And the final simulation that I'd like to show you is a basic analysis of the trunnion or lifting pin that's attached to these casks. These are typically bolted to the sides of the cask, typically 2 on either end, and are used to allow the lifting hooks to attach to. Although not as exciting or dramatic as the other simulations, these are obviously quite important. On the left here is the typical finite element model, and the right image showing the stresses due to that loading from the lifting, which can then be compared with the known yield properties of the material. And that is used typically to demonstrate the requirement for the regulation of a safety factor of 3 on yield. With that said, this concludes my presentation on the simulation of the casks and their contents. What I've tried to show you here is impact analysis, some static analysis, thermal stress analysis, all these disciplines necessary in the treatment of these casks. Hopefully I've demonstrated the power and the value of these offerings that we have here with MSC. And I'll be happy to answer any questions at the end of this webinar. So thank you, and at this point I'll turn the controls back to Srinivas.
Thank you very much, Doug. At this time, I would like to talk about another but very important aspect of simulation process, namely the data and process management. Let us first start with a question. So how is simulation generally used within engineering departments? So organizations have different needs and starting points leading to different levels of engagement over time. The lowest level of engagement is what could be called the event-driven simulation. For example, a product fails for no obvious reason and one wants to investigate why. You would send it to an analyst and he or she will figure it out. Simulation is of very good value in this case, but if it is not applied until after occurrence of a problem, then it would be more expensive to eliminate the problem, and then it would have been if it was avoided at the very beginning. And by the way, this mode can be done in-house or through services provided by an external partner. A step forward is making simulation an integral part of the design process. This helps to identify issues earlier, leading to cost savings and improved products. The next level involves automation of the simulation process and customization of user interactions to allow more people in development to use simulation in a more reliable and an efficient way. It also ensures that best practices are followed all the time. And the topmost level involves better sharing of simulation results for decision-making among all involved in product development, and depending on who should have access to the data. It also allows for quicker access to historic data and reuse of the know-how. No matter which level you start at, it is important to consider simulation tools that make it very easy to migrate to other levels to get the maximum benefit out of the simulation process. MSC offers solutions that address needs of companies at each of these levels that we talked about. The solution set also helps users transition from one stage to the next. MSC offers easy-to-use simulation environments designed to support both expert analysts and casual users. It addresses the need for accurate multidisciplinary simulation as well as tight integration with CAD systems. The unique template studio helps the enablement of non-expert users. Template Studio lets expert users to graphically edit captured methods so that they can subsequently be improved, transformed into more generic capabilities, or used by designers to perform the same type of simulation on the new product versions that they are working on. For example, by using the templates, the various Cask test simulations that Doug discussed can be automated, saving both pre-processing and post-processing time, and also let users solve more configurations much earlier in the design cycle. The use of templates offers several benefits to the engineering and development process. Template automation brings significantly improved simulation speed and turnaround, which shortens design cycles and time to market, often a key competitive advantage. Accurate simulations that reliably deliver comparable results support the creation of optimized solutions featuring improved performance and increased reliability at a lower cost. Virtual test results, accessible and shared between all participants in product development, allows for better and faster design decisions based on an enhanced understanding of product performance early on in the design cycle. Last but not least, the ability to capture and reuse best practices and engineering know-how increase development productivity. As a side effect, it also helps to retain valuable corporate know-how when people retire or leave for other reasons. Using simulation often creates a lot of valuable data. This data could be any type of data that is relevant to simulation. All of your models, model configurations, CAD/CAM files, any kind of CAE files, simulation results, requirement documents, material properties, or load cases, or could even be non-CAE type of files, such as Word documents or Excel spreadsheets, or some other templates that you have generated. If these massive amounts and the various types of simulation data are not managed effectively, it could result in poor reuse and knowledge sharing, in addition to communication and process inefficiencies within the company. So the real challenge is to get the simulation work done better, faster, and cheaper, and be able to run more and more simulations and improve the credibility of simulation by having a complete audit trail of the information, linking results back to the design alternative that has been analyzed. Sim Manager from MSC.Software offers the possibility for everyone to collaborate and get their simulation work done better, faster, and more reliably. In IT terms, it is a web-centric framework for sharing, collaborating, integrating, accessing, and controlling the simulation data and processes. Our solution represents a software infrastructure that will securely store, protect, and tie together all of your simulation activity. It is built using a services-oriented architecture, making it easy, extensible, and customizable to meet your needs. Through this web-based platform, your simulation data will be securely available around the globe, 24/7, version-controlled, and with secure role-based access control. An exclusive in-depth webinar will explain in detail the features and benefits of this simulation data management system presented here. And there is one scheduled on April 7th and another on June 2nd. To register for any of these webinars, please visit the MSC website. We have discussed the simulation software offering from MSC and also the simulation process management pieces from MSC. I would also like to point out the final and another important aspect of services offered by MSC. The worldwide MSC services team has a pool of over 200 engineers with a broad variety of industry experience. This team is available to perform one-off projects using MSC.Software and hardware resources, or to perform proof-of-concept projects to help leverage software sales and your software investments, and to train and transfer the know-how on the use of our simulation technology to current customers. The team also can help with customized process automation and web-based engineering process and data management across a customer's enterprise. So let us briefly review what we have so far covered in this webcast. We looked at how MSC solutions are applied to address one of the important problems faced by a nuclear power industry, namely the design of nuclear spent fuel cask. The capabilities to simulate impact and crash, heat transfer and the thermal stresses, and welding and residual stresses, they all make MSC's products ideal for addressing a cask design problem. We have also reviewed the MSC solution spectrum that spans across multiple simulation disciplines and also the simulation and process data management. I would like to reiterate a couple of key values provided by MSC. First, MSC offers flexible and a complete solution set to address nuclear power plant simulation needs. Depending on your goals for simulation, you can choose from conventional, proven engineering products to an environment offering highly automated simulation process, including the simulation data management. And second, MSC offers efficient solutions for drop test, sloshing, thermal management, or mechanical system and control simulation. Considering the challenge of building even the larger structures in the future, the capability to understand and avoid fatigue and other failure issues before building the first prototype will help reduce the maintenance and repair costs, thereby increasing the possible return of investments for power plant manufacturers and suppliers. In summary, simulation allows nuclear power plant manufacturers and suppliers to perform tests early and repeatedly in the development process. This enables you to find design flaws before they get really expensive and bring new, more reliable and safer solutions to market in a shorter amount of time. Before closing, I would like to draw your attention to MSC's virtual product development conferences being held around the world starting in April. This provides an excellent opportunity for you to interact with other users or MSC team in support and services and product development, along with a chance to attend some free training sessions covering some either nonlinear analysis or mechanical system analysis. Please check out MSC website for more information and to register for any of these conferences. Once again, thank you very much for attending this webcast.